In today's tutorial, we're going to do some problems on double integrals and some applications. Now, as you know, as you may know, the zoom on this is broken. Okay, so what I've done, I've got a secret weapon: A3 paper and thicker textures. So bear with me. I'm crossing my fingers and I hope it's going to work. But obviously the font here is quite small. Okay, so you might just have to look up the questions in front of you in your course pack. But I'll write down the general gist of the question anyway. So what we'll do is we'll look at a few basic double integrals. We'll look at how to reverse the order of integration. And also we'll look at some applications too. I think there's a question on centre of mass or something like this. So we'll gradually go in nice and easy, and then we'll move on to the harder parts. Okay, so let's see if we can do this. Oh, start over there. How's that? Can you see that up the back? Yes, good. All right. All right, 100B. You have the following. Function of two variables. Defined in this way. And our region of integration, our two-dimensional region, is the set omega. And it's the following set of points. It's those x and y values in the xy plane such that x squared plus y squared is less than or equal to 1, and x and y are non-negative. So, one of the sort of requirements in your course pack at the start of this section is you need to draw a picture for each question involving double integrals, a picture of the region of integration. So in this case, we want to sketch the set omega. So what's the set omega going to be? Yeah, it's going to be a quarter of a circle, right? So it's like a disc with just 1/4 left over. Okay, so if I wanted to sketch this, I'd draw in my circle x squared plus y squared equals 1, which will be something like that. And then I realise that x is non-negative and y is non-negative. So this would be our region of integration. Now, the first thing we would see, we would think for this kind of region, it's a polar rectangle, right? So we would think maybe polar coordinates. But I'm not going to start with polar coordinates because they're quite challenging. So I'm just going to do this in just the regular way without using polars. Okay? So what we need to do is somehow describe this region here. So let's just let I be the double integral of our function over our region omega. Okay, now I'm not going to describe the region omega using polar coordinates. Okay, the way I've done it, this curve here is going to be y equals 1 minus x squared, root 1 minus x squared. So what I can do is just draw, say, this vertical line. The vertical line enters the region at y equals 0, and it exits the region omega at y equals root 1 minus x squared. So, in terms of our description of omega in terms of, I guess, bounding functions, y is going to be greater than or equal to 0, but less than root 1 minus x squared. What about the x bounds? What are they going to be? Yeah, 0 to 1. So all I need to do is take this vertical line and shift it and see how far I need to go along the x-axis to cover the entire quarter disk. So it would be between 0 and 1. Okay, so now what we want to do is put this into a double integral. We know that we can use Fubini's theorem to write I as a repeated integral. So by Fubini's theorem, I is just the following iterated integral. Remember, the constants go on the outside. Now, is it dy dx or dx dy? Dy dx, because y is between these two functions and then on the inside. Okay, so it's not that hard to integrate now. You do the inside integral first. So you imagine all the x's are constants, you integrate with respect to y, plug in the limits of integration. Then you move to the outside integral, integrate everything with respect to x. So let's do this. So if I integrate with respect to y here, I'm going to get x squared y squared on 2. This is going to go to y to the 4th on 4. Okay. So now I need to sub in my limits of integration. Well, when I sub in y equals 0, this is obviously going to be 0. And when I sub in root 1 minus x squared, I notice that the square root sign is going to disappear. Because I've got y squared there, that'll take care of the square root sign, and y to the power 4. So, if I substitute this in, I should get something like the following. I'll get x squared 1 minus x squared all over 2 plus 1 minus x squared all squared over 4 dx. So all I need to do now is expand the brackets and or simplify it in some way. And all I've got now is a single integral. Okay, so according to my calcs, after the simplification, you'll get something like this. Okay, 1/4 minus x to the 4th on 4 dx. And if you integrate that, you'll get 1/5. Okay. Any questions? I can't actually move the paper up and down, it's too big. So I've sort of got a fixed writing space. Okay, well, what's that like on the difficulty scale? Well, I'd say medium. It's not super easy, it's not super hard. Okay, I'm going to move on to one where you need to reverse the order of integration. There's a whole bunch down here in question 101. I did one of these in lectures. I think I did C in lectures. I'm actually going to do part B. Now, can anyone suggest, well, let's write it down first before I ask some questions. Okay, so we want to evaluate the following integral. Now, why can't I do that integral straight away? Why can't I just do the inside integral then the outside integral? Why can't I just integrate e to the x squared with respect to x? What's the integral of e to the x squared? The antiderivative. It's not e to the x squared all over 2x. Well, there is no antiderivative for e to the x squared with respect to x in terms of elementary functions. So you might think, oh, okay, I'll just do the inside integral. Well, what's the antiderivative of e to the x in terms of elementary functions? Doesn't exist. Okay, you can grind it out using some sort of series if you want to, but that's not an elementary function. But if I could switch the orders of integration and adjust these, then I could easily integrate e to the x squared with respect to y. Okay, what's the antiderivative there? Well, it's y times e to the x squared. Okay, I can do that. That's no worries. So let's try to switch the order of integration around. Now for that, we need to firstly draw a picture. So let's try to work out what our region of integration is. Well, omega is just, all right, well, y is between 0 and 1, and x is between y and 1. So let's draw a little picture and see if we can work out what's going on. Okay, so I'm going to draw in the lines y equals 0, y equals 1. So y equals 0 is there. X equals y and x equals 1. So I've got the line y equals x there. Okay, so which triangle is it? Is it the upper triangle or the lower triangle? The lower one. Why? Well, let's draw a horizontal line. The line enters at this line here, at the line y, and it x equals y, and it exits at x equals 1. So hang on, I think I've got the... Oh no, that's all right, yeah. So it's definitely got to be that bottom region. Okay, so now what we want to do is redescribe that region somehow. Well, let's draw the same picture, but instead of using a horizontal line, let's use a vertical line. Okay? Now I'm just going to relabel this instead of y equals x, x equals y, y equals x, 1 and 1. So here's our region here. So I'm going to use a vertical line to look at the bounds for the y values. So we want to redescribe my region omega. It's the same region, we're just describing it a different way. So what's the region going to be? Well, you can see with the vertical line enters at the line y equals 0, and it leaves the region at the line y equals x. Now to trace out the whole triangle, I need to move between 0 and 1 on the x-axis. So what's y going to be between 0 and x? So now, we spent all that time redescribing, drawing pictures. Now we can actually use it and put it to work. So, I is just the double integral of this function over omega. Fubini's theorem says that, okay, I can write this as a double integral, either like that, like we had at the start, or using this setup here. So I'm going to use this setup because I'm going to reverse the order of integration. Okay, so y is between 0 and x, so the dy will go next, and then the dx. So now, what I can do is perform the inside integral first. It's going to give me the indefinite integral is going to be y e to the x squared. Sub in these, I'll get x e to the x squared dx. Okay, I've left out one line there. Now, I can integrate x e to the x squared. What's that going to be? Right, exactly. Just 1/2 e to the x squared. If you want to do it the long way, you can use the substitution, u equals x squared. Don't do it by parts, though. I wouldn't recommend that. So when you plug in x equals 1 and x equals 0, you'll get something like this. Yes. Somebody in cat eye said more smiley faces, please. So I'm happy to oblige. Somebody in cat eye also said, what changes would you recommend? Chris should get an iron for his shirts. It's true though. It's true. It's true. Any questions for this one? Now, it looks simple when I do it, right? But there's actually a fair bit of working there. Can you see how you really need to be on top of sketching the regions? That's the important thing. Sketching them and mathematically describing and redescribing them. So that's a middle of the road one. That's a middle of the road one. I'm going to move on to 102. And then we'll have a look at 104, I think. Here we've got another integral, and we want to first change the order of integration. That's what we're asked to do. So let's see how we go with this one. That's 102. So I'm going to let I denote our integral, the value of our integral. And the question asks us, when you may be able to integrate that straight away, but the question asks us to first change the order of integration. So, our region of integration, let's call it, I don't know, omega or something. So, x is between 0 and 1, and y is between x and 1. Got the feeling this is going to be a triangle. So let's draw a picture. Remember, drawing a picture helps us geometrically focus on the region, and then we can redescribe it. Okay, that's the motivation for drawing a picture. It just gives us a better geometric understanding of the region of integration. Okay, so let's draw in the lines x equals 0, x equals 1, y equals x, and y equals 1. Okay, now which triangle is it? Is it the top triangle or the bottom triangle? Top, right. Okay, if I look here, I just draw my vertical line. The vertical line has to enter at x and leave at y equals x and leave at y equals 1. So that would align with what we have here. And of course, you have this little interval down here. So our region is the top triangle. So let's redescribe our region of integration omega. So I'm going to draw another picture. Drawing the same lines. All right. So here's y equals x. Okay, who wants to have a go just at redescribing that region? Instead of a vertical line, I'm going to use a horizontal line. So what's the redescription going to be for the bottom setup with our horizontal line? Who can tell me? What's it going to be? Yes, x is between 0 and y because the horizontal line enters the region omega at 0, the line x equals 0, and it leaves at x equals y? Yes, y is between 0 and 1. Great. Okay, so now let's set up our integral in terms of this description now. So this is just a double integral. And Fubini's theorem says I can write my double integral as a repeated integral over these type of regions. So I'm going to use this description. Now, you can see one of the advantages of reversing the order of integration here. It's easy to integrate that inside integral with respect to x. Okay, so that's one advantage. So let's do that and then work our way onto the other integral. So if I integrate the inside integral, it's just going to be x, with respect to x, it's just going to be x times all of this. And when you substitute in y and 0 for x, I'm just going to get this. Now, I've got one slightly challenging more integral to do. What's the antiderivative of this integrand? Well, it's going to be something involving a square root sign. It's going to be something involving 1 minus y squared all square rooted. Well, what? going to be, yeah, it's going to be something like, if it's going to be something like this, right? It's going to be something like this. But not quite, right? If I differentiate this, do I get this? Well, almost, except if I differentiate this, I've got this minus coming to the front. So I just need to adjust with a little minus sign there. Okay? Now, if you're not familiar with that, again, you probably could do this using a substitution. You would let u equal 1 minus y squared or something like this. But, you know, your second year now, we expect you to be able to do those sorts of things. Okay, so if I sub in 1, I'll get 0. If I sub in 0, I'll get minus 1 to the all to the half, which is just minus 1. Oh, sorry, minus 1, yes. Yes. Now, of course, you may be able to do that integral and just integrate straight away. That's okay too.